So our speaker today is Margarita Marinova, and she's just graduated from Caltech, where she did a project on one of the biggest dilemmas still facing planetary science at Mars, and that's the origin of the Martian dichotomy. So Margarita has investigated this phenomenon from a particular perspective, and today she's going to tell us about her results during her PhD research and what she's looking at now and the new questions that are raised by her work. So if you'll join me in welcoming Margarita.
Thanks, Adrian. Thank you all for coming, and can everybody hear me? Just to start off with that. Okay, thank you all for coming, and as Adrian mentioned, I'll be talking about the Mars dichotomy. Now I'm going to leave the best for last. So don't worry, it's coming, but I'm going to go through a lot of the background work that really sets up the stage for understanding the dichotomy with respect to large impacts. If you have any questions at any point, please just stop me and ask. That would be great. So the main topic here is planetary scale impacts. For those of you who know what the dichotomy is, so the dichotomy is about 40% of the Martian surface. In order to actually make a feature that big, there has to be some very large process. In this case, I'll argue that it's impact, which means that it has to be a pretty damn big impact. So this is work, as Adrian mentioned, that I did at Caltech with Odette Aronson, who was my advisor, and Eric Asfog, who is at UC Santa Cruz, and I'm currently at NASA Ames. And this, by the way, is an actual image of one of the simulations, which was made pretty, but it's actual data from the simulations. So impacts are something that we've thought about for a long time. Even when you just look at the moon with your naked eye, you can see all these various circles on it, anything from the smallest ones that you can see to very large basins, and all of these are impact craters. And impact craters are interesting and have taken up a lot of study time because there's such a huge variety of them. So you can start from the micrometeorites. This is something that, for example, the space shuttle is most worried about, small grains hitting. We hinge our wishes on tiny little grains of sand flying through the atmosphere. For slightly bigger impacts, people are usually pretty familiar with Meteor Crater in Arizona. And this crater is actually sort of the example child of especially small craters. You can see that it has a raised rim, it has a very nice bowl-shaped, and it looks the way we would imagine impact craters looking. The reason why it looks so perfect is because it's so young, it's in the desert, it hasn't been eroded very well. We actually have very few examples of such nice-looking craters on Earth today, and so that's one of the reasons why it's studied so much. When we go for slightly bigger impact craters, Chicxulub is one of the other very famous ones. This, of course, is the one that hit in the Yucatan and caused an impact that we think killed the dinosaurs. Now, if you look at my little scale of impacts, you'll see that I still called it a pretty small impact. And when you look at it, I mean, that circle is pretty small compared to the size of the planet, to most countries, all of that. Now, granted, the dinosaurs thought it was a rather bad event for them. But on the general scale of impact, it's actually not that big of an impact. The largest impact structure that we have on the Earth is actually in Southern Africa. And when you look at the continent, you think, okay, big, I should be able to see it. You can't see it from any picture like this. If we zoom into this area, which is this picture, it's actually this impact crater right here. It's very hard to see because it is very old, which means that it has been eroded quite a bit. If you look at the central area, so right around where the star is, this is actually, you see some of the folds around the central, where it went up and then collapsed. So you can see some of these folds, but basically we can look at geologic evidence to say that this was an impact structure. This is the largest impact structure that we have on the Earth. Now, the other large impact that we're very familiar with on the Earth is the moon-forming impact. In this case, we had an object which was about the size of Mars hitting the Earth, so something half the size of the Earth hitting into the Earth. A lot of material got spewed out in the process, so this was an off-axis impact. A lot of material got spewed out. This material then eventually coalesced into a ball, forming the moon. And the really important consequence for the Earth was that it reset the entire surface of the Earth. After this, it's considered that the Earth was just a molten ocean of magma. And so it really reset anything that happened before that. We wouldn't really have a good record of, because it just reset the whole surface. There was that much energy in that impact. What I'm interested in is the impacts that fall in between. So something that's not a little circle on a map, that doesn't, on the other end, it doesn't actually reset the whole surface, but is in the middle. These sorts of impacts happened a lot at the end of accretion, when we had still large bodies floating around and they were impacting the planets at the final accretion stages. And what really sets them apart are four main things that I'll focus on throughout the talk. So one of them is that surface curvature is actually important for these impacts. For the smaller impacts that I was showing you, all the simulations, all of our understanding of them, we assume that it's a flat surface, right? When we're sitting on the surface of the Earth right now, we don't really care that it's curved. It looks pretty flat. So for these smaller impacts, you can assume that this surface is flat. But once you actually get into larger impact structures, that curvature of the surface is very important and has an effect on how the whole impact process proceeds, how the material is redistributed, what we see on the planet afterwards. Combined with that is also the radial gravity. If you imagine that you have material being ejected from an impact, well, the curvature matters, right? If you just have a flat surface and it tries to skip, it will hit somewhere else. If the surface is curved, that material will actually impact somewhere completely different on that surface, a different distance. The radial gravity also matters with respect to that. In our simulations, the relative size of the impactor is large compared to the size of the planet. Now, that has a lot of consequences, but one of the main ones is that if you have an off-axis impact, so you're not hitting the planet straight on, but at an angle, your entire impactor might not actually hit the planet, right? Because it's so large, part of it can actually miss the planet and just keep going and pretend that nothing happened to it. And so the way you actually put energy into the planet and distribute that energy is very different because of the large relative sizes of the impactor and the planet. And the last thing is that we're really looking for where there's no global resetting of the planet. We want to have some signature left of this impact. So why study these impacts? Clearly the Mars dichotomy would be one question, but we actually see these very large impact structures all over the solar system. Basically, any solid body has them. Here are some examples. This is the moon and South Pole Aitken Basin on the moon, which takes up about 30% of the moon's surface. There's Caloris Basin on Mercury and Herschel Crater on Mimas. I can keep going on and on and on. As I mentioned that these were the large impacts that occurred at the end of accretion, it's not surprising that they're all over the place. And so really understanding how these impacts form and what their consequences are can tell us a lot about the formation, about the end of accretion stage of solar system formation. So another thing is that because these impacts have so much energy, they're carrying so much energy with them, they have global consequences. They can remove a lot of crustal material. If you think of the explosion that actually excavates a lot of the crust and puts it all over the surface of the planet, because of the high energy, they can melt a lot of the surface. They can deposit that energy at different places in the planet, and I'll talk about that later. They can change the rotational period of the planet. You know, remember, we're talking about really large objects. When you have an off-axis impact by one of these objects, you can actually contribute a lot of angular momentum to the system. And on top of that, it's mass accretion, right? When you have an object that's a few thousand kilometers across and you smash it into Mars, you're going to add a lot of mass to the system. And throughout this, you also notice that I'll be talking about scaling laws to some degree. And one question there is, when do we start going from small impacts to these planetary scale impact size regime? There has to be some point where the small impact crater scaling laws no longer apply when you get big enough. And that's one question that we're trying to answer with this work, is when is it really its own regime of impact cratering? So just a little bit about the general impact process, just to get everybody on the same page. We have a lot of intuitive understanding of this because everybody has thrown pebbles into water. And so we know basically what it looks like. It's a very similar process, just think of things actually eventually freezing in place because the material that you're hitting into is a solid rather than just water, so it freezes in place. But it's exactly the same process. So you have the impactor coming in, it sets up a shock wave. The shock wave propagates through. It starts excavating material. As it propagates through, there's also a rarefication wave, a reflection from every point that it hits, that travels back. This rarefication wave expels material outwards. It accelerates it towards the surface at an angle. And so this is what makes this material be ejected outwards. As the material is ejected, it falls back onto the surface, and it forms this crater rim here that we saw in meteor impact crater, and then a bowl-shaped cavity. It's very intuitive, it's very simple. When you get into the physics of it, not so simple, but intuitively, it's very simple. And just keep thinking back to all of these intuitive concepts as I talk about what actually happens in these planetary scale impacts. What I looked at was actually a large parameter space of planetary scale impacts. So remember that we really want to understand how these work fundamentally. What are the features that they produce on the planets? Why do they produce all these features? And it's interesting because we do see them in a variety of planets and settings. And so understanding how the features change with impact angle, velocity, energy, and the type of material is actually very important. So those are the 4 specific parameters that I investigated, and I investigated a range of them. So impact energy, just 1/2 mv squared, just the kinetic energy of the impactor. We looked at this over 2 orders of magnitude in energy. I actually looked at a high energy too when I was trying to smash Mars to pieces. I never succeeded, unfortunately. We're also looking at a range of velocities, 6 to 50 kilometers a second. So 6 kilometers a second is a little above Mars's escape velocity, so about the mutual escape velocity of a large impactor and Mars. And then 50 kilometers a second is twice Mars's orbital velocity. So if you had an object which was going in the opposite direction from Mars, that's the largest velocity you could actually hit Mars with. And I want to emphasize again, these are simulations into a Mars-like planet. So that's important to keep in mind. It's a Mars-like planet. Then the angle of impact, this is something that's really important. A lot of impact simulations, and especially impact experimental work, is done at head-on impact. So you have the surface, you hit it at a 0-degree angle. Well, if you actually look at the probability of what angle you would hit an object with, it's actually normally distributed around 45 degrees. So the most likely impact angle is 45 degrees. It is not 0 degrees. And everything changes quite a bit when you go to 45 degrees. Now, there has been some work that has been done at off-axis impact angles, and that's very important. But here, this is why we really wanted to investigate all kinds of angles, because it's so important to look at the whole range and not just an angle that has a very, very low likelihood of being the true case. And then we also looked at 5 impactor types. We looked at basalt, which was the starting material that we looked at, even though it's not overly realistic that you would have a 2,000 kilometer impactor made out of basalt. Then we looked at olivine, a differentiated impactor, and iron. So you can think of this as the spectrum of, you have a large object with no core, you have an object which is half the diameter is core, half the diameter is mantle, and then you have an object which is all iron. And clearly, the end cases are not highly likely, but it really gave us a range of what the possible outcomes are for these sort of impact conditions. And then we also did this undifferentiated case, which is, so in the differentiated case, we assumed that half the diameter is an iron core and half the diameter is an olivine mantle. In the undifferentiated case, we made up our own material, but the basic idea is to think of it as, well, what if everything is still mixed? Differentiation doesn't actually happen quickly, since we still don't fully understand when differentiation happens. Let's say these impactors are still mixed up iron and olivine because they haven't had a chance to differentiate yet. What would happen then? So these are the types of impactors that we used. And all of this work was done at the SETI cluster at Caltech. I think I ran on the order of 1,600 simulations, something like that. So props to all the guys down there who work and helped me run everything and made it work. Sorry, I already talked about this. Just the only thing I'm going to point out, for the range of energies and velocity that we used, this is the size range of the impactors. So very, very large impactors. And remember that Mars's diameter is about 7,000 kilometers. So very large impactors. So a little bit more about the modeling before I get into the results. We used a fully 3D model. This was important so that we could actually simulate these off-axis impacts. Otherwise, that's pretty much impossible. So we used the smoothed particle hydrodynamics code, which has been used for a lot of applications, but specifically it was the code that looked at the moon-forming impact. And Robin Knapp and Eric Asfog were the ones who did that. There's only gravity in the code. There is no strength. These impacts are far into the gravity regime of impacts. Strength will certainly play some role, but it should be a minor change to what actually happens. Most significantly, it would matter for how, well, when we look at the final structure, there'll be some slumping. Some of the material will move just depending on the strength and exactly how, what the final shape of the structure is. Now, because the size of our impacts and impact craters are so huge, this should be a very small effect. But we don't have strength. We don't think it makes much of a difference. But it's something that needs for you guys to know. It's a Lagrangian code, which means that we use particles. It's not a Eulerian code. You have a grid, and each grid, you have properties for each grid. In our case, we use particles, which is why this is what the picture looks like. The reason for using particles is because you see the planet, which is all in nice, and you could use the Eulerian code for that. But then there's all this empty space. And we still need particles to fly through the empty space and do their thing, but you wouldn't want to simulate all that empty space because it would just be wasted computational energy. So using particles is actually a very good way for simulating these dense objects in nothingness. And the resolution that we're using is about 120 kilometers. So that is certainly pretty large, and that's especially something to keep in mind when I'm talking about the removal of crust and the change in the crustal thickness. The crust on Mars is thought to be about 50 kilometers on average. This is much larger, but again, you'll see when I look at things, I look at the removal of crust, the complete removal. So if we can remove 120 kilometers, we can certainly remove 50 kilometers. And this is actually a much higher resolution than most other simulations. Just to put in perspective, we're using about 200,000 particles, which means that one of my simulations runs for about a month before it's done. So. And the other really important thing is that we actually put a lot of effort into making a realistic early Mars. A lot of the previous simulations, and including the moon-forming impacts, there was a planet made and it was basically accurate, but it wasn't really accurate. What I mean by that is a lot of the internal energy properties were not exactly accurate. The size of the core may not have been exactly accurate. Either the size of the core or the size of the planet itself may not have been exactly accurate. In our case, partly because we wanted to simulate dichotomy, but also more importantly, we wanted to look at melt. If we don't have the correct initial conditions for the internal energy, we can't really look at melt. And so we put a lot of effort into this. We made our own equation of state because we wanted to specifically use olivine, which was appropriate for Mars. So we made that, and then the size of the core is appropriate for Mars, the internal energy is appropriate for Mars. It's a pretty good Mars that we're smashing things into. So this is one of the simulations that I'm going to show you. This is actually the dichotomy forming impact. But this is Mars. This is the impactor. The color is actually the internal energy of the object, which is, at the surface at least, is pretty equivalent to the temperature. Our impactor is colder. That's why it's redder. So the yellow colors are hotter. So impactor comes in at a 45-degree angle into the planet at about 6 kilometers a second and hits the planet. Okay, so you see the impactor comes in. It basically bulldozes a lot of the material in front of it, spews a lot of the material out. The planet gets a little disturbed here. the material then swings around and re-impacts onto the planet. So here, the white particles are really hot particles. The redder particles are colder particles. You see a lot of material going around. I'm just going to play it one more time. But one thing I want you to notice that even though a lot of material goes around, these areas, this and on the other side, don't actually feel very much. I mean, they get some material impacting on them, but overall, they stay reasonably cool. And most of the material goes around and just redeposits downrange of the impact location. And you...
Sorry, how long, what's the actual time scale from start to finish?
Oh, that's a very good question. I'm going to guess this is on the order of an hour. Yeah, they're very fast, very fast. I mean, if you think about it, that impactor was moving at 6 kilometers a second, right?
The shock waves
So.
around the planet look really high. I mean, it's a
Yeah.
substantial diameter fraction of its radius.
Yeah.
It's a bad day for me.
Yeah. Yeah. So one thing that you may have also noticed is the planet, you can see the planet rotating after this impact because of all the angular momentum that's deposited into it.
But is the planet fixed somehow?
Sorry?
You don't have a recoil in the planet, right?
No.
It's fixed.
It's not, what do you mean by fixed? It's not fixed. The frame of reference gets shifted always to the center of mass. So 0, 0, 0 is center of mass, but it doesn't actually affect any of the physics or anything else. Do you mean if it gets knocked off of its orbit?
No, it's just, it looks like that the center of the planet is roughly at the same place all the time.
Well, that would be true because even though the impactor is pretty large, it's still only on the order of a few % of the planetary mass. Yeah, so it wouldn't change very much.
Was Mars rotating prior to the impact?
No, that's a very good question. Mars starts completely stationary. It is not rotating. Yeah.
What's its rotation afterwards?
I will get to that. Yes.
You mentioned that some of those areas are relatively undisturbed, but they look like they're moved pretty quick. As the shockwave passed through them, any idea what the acceleration was relative to basically the radial acceleration of some of those areas?
I don't know the exact radial acceleration. I know that in areas other than the specific impact area, the movement for the more energetic impact is on the order of 100 or 200 kilometers. Radial movement of the planet. It's only a few % of the size of the planet.
Could you say something about the temperatures?
The temperatures, no. We looked at whether material is molten or not molten, and also the amount of vaporized material. The amount of vaporized material is only a few % of the molten material. We didn't specifically look at temperature, partly because a lot of our interest was in subsurface material, and there going from internal energy to temperature is not quite as easy. But does that sort of answer your question?
Well, just go on.
Okay. Okay. So here's a quick summary of the different aspects that I'll talk about, which I think we pretty much covered right now. So looking at the surface features, one question is, how does the crustal redistribution work, especially since we have this curved surface, and so the actual travel distance of the material is very different from what we would expect on a flat surface from an impact. Is a rim formed? So in small impacts, there's always a rim. So in this case, is there a rim? What is the shape of the crater? For smaller impacts, it's always a very circular crater. Does that change with more energetic impacts and planetary scale impacts? And the surface melt, again, we're looking at whether the whole surface is reset in these impacts. For the planetary interior, we want to know whether there's mantle melt, how much of the melt is actually in the mantle, whether there's internal mixing within the planet. And then we're looking for the whole planet effects, which are accretion versus erosion. Is it always, a lot of accretion simulations for the solar system actually assume that anytime two objects impact, there's full accretion, 100%, nothing gets lost. So we're going to look at whether that's actually true. And then what's the new rotation rate from these impacts? So here are some, looking at this rim formation and where the material gets redistributed. Remember I mentioned that our resolution is much larger than the actual crustal thickness. This is why all of these maps are relative crustal thickness. So it's looking at the current thickness with respect to what it was when the simulation started. So at the beginning of the simulation, the average crustal thickness is about 150 kilometers. What is it with respect to that? We think that these are quite robust in terms of what they show and what these look like. And we also did simulations with different resolutions. So we actually looked at 150 and 180 kilometer particles. And what we find is very, very similar. In none of these cases do we find very different results for these different resolution types. So I think you can, I'm happy to present these with quite a bit of confidence in terms of what they show and what would actually happen if we had infinite resolution. Okay, so here we're looking at a pretty low energy, slow impact, and you see that we formed this impact crater. All of this blue stuff is where the entire thickness of the crust is removed. So the impactor completely penetrates through the crust. In this case, the penetration depth would probably be about 500 kilometers. So goes pretty well into the subsurface, excavates the material, and puts it on the surface. This is the entire surface of Mars, so to orient you. And you can see that there is effectively a crater rim that is formed around the planet. And remember that all of these images are 24 hours after the impact. So I'm not talking about relaxation on the multi-hundred million year time scale after this happens, but this is right after the impact. So in this case, even for this relatively large energy, we actually see features which are pretty similar to these smaller impacts. Now, once we get to much more energetic impacts, things change. So here, both of these impacts are the same energy and a slow velocity again. This is one of the higher energies that we simulated. There are two different material types, is what the big difference is. And for the undifferentiated one case, you see that a lot of the material, so most of the surface of the planet is actually covered with extra material. We don't see a very distinct rim around the cavity, but it's rather a more uniform thickening of the entire crustal, of the entire surface. In the case of the iron impactor, we do actually see a rim-like feature that forms around the crater. The other thing we found is that actually for higher velocity impacts, even for the highest energy, for high velocity impacts, we had a rim forming around. Our theory was that actually it's the size of the impactor that matters, right? So in these cases, we're keeping energy constant. So as we change the velocity, the actual size of the impactor changes. And so we found that for smaller impactors, we got something that resembles a rim. We also got smaller impact craters. And then for larger impactors, we actually don't see a rim. We see more of a uniform crustal thickening. You may be wondering what these little dots are. This is actually an antipodal crustal removal. So the shock wave that was going through and making Mars very unhappy.
What is the basalt target?
It's not energetic enough. The shock wave is not strong enough by the time it gets to the other side. Yeah. 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 The shock wave basically propagates through, and at the opposite end of Mars, it still accelerates the material to such a velocity that it's above escape velocity, and it just gets removed and excavated. Now, that question about what the shape of the actual cavities is. As I mentioned, for small impacts, these cavities are very circular. Even in experiments where we've done very oblique impacts, they're very, very circular. But we actually see that for large impacts, you can get pretty elongated cavities for relatively, so this is a 45-degree angle. I'll show this a little in more detail later, but for small impact craters, you have to get to 85 or 80, 85 degrees, so very oblique in order to get an elongation in the craters. But here for planetary scale impacts, you can actually get elongated cavities even for 45-degree angles. And in terms of the crustal redistribution, you can see that in oblique cases, the material gets redistributed usually downrange of where the impact crater is, and does not form a rim-like structure around it. So for very energetic impacts, a rim only forms when it's lower energy and also more head-on impacts.
What's the size of your SPH kernel on these figures? Resolution of your
30. Yeah, 2 degrees. Thank you.
Can you repeat the question?
Yes, sorry. What's the size of the particle on this map? And it would be about 2 degrees. So 1 degree on Mars is about 60 kilometers. So 180 kilometers, 2 degrees. Yeah, so 15 particles per one of these. Oh, and this is, some of them do really interesting things. So this is the highest energy that we simulated, a slow impact and 45 degrees. So what really, and differentiated impactor, so what happens is that the iron core has so much momentum in it that it literally just skims the surface of the planet and keeps going, keeps bulldozing everything in front of it. So you can get a lot of interesting things.
Why is there such a difference when there's iron?
Because it has higher momentum. It's not stopped as easily. So they're actually, it's interesting because there's two competing ones. So in this case, it's because, so this main cavity, similar to this, is formed by the olivine part of the impactor. Then the iron part of the impactor just keeps going. It's like, olivine, I don't see you. Okay, you slowed me down a little bit, but I'm just going to keep going. And so it just keeps plowing through. And then in the case of this one, it's very similar. So the iron impactor just keeps going and stopped. Yeah. Well, so it has higher momentum per unit area, effectively, right? So it doesn't get stopped as easily, but because it has higher density, it eventually sinks. While the olivine part of the planet is capable of mixing. We actually find that it doesn't mix, but it's capable of at least mixing. It's not obvious where it would end up. The iron part, it plows through and then it sinks. Okay, so the general conclusions for crustal redistribution are that with the increased surface curvature, that also, with the presence of surface curvature, that actually increases the ejection distance of the material, which also makes it have a more even distribution over the surface of the planet rather than forming a rim around the crater. And we see this downrange thickening of material for more oblique impacts. Now, a question in impact cratering is always, what formed the crater? When we look at craters on the surface of other planets, what velocity, impactor type, impactor size, energy, angle formed that crater? And in a lot of cases, you can't really disentangle all of these aspects from each other. You can say, well, if we choose this energy, then here are the velocity and angle that formed it. For these large impacts, one thing that we could possibly use in the future, and once we send people to Mars, maybe actually check whether the dichotomy was formed by a large impact, is looking at the geochemical signature. So a lot of the accretion studies for solar system simulations have shown that the impactors are pretty geochemically distinct from each other. And so from this actually, so in this case, we're looking at green is Martian crust, blue is Martian mantle, and red is the impactor. And so these are RGB plots. So purple would mean blue plus red. So it's a mixing type thing. If we look at this, we can see that at the specific impact, we can see the crust is not very much disturbed. It doesn't have a lot of material from other sources on it. We can see the mantle, and then we can see where the impactor material is actually located within the crater and also around the crater. Oh, I should mention that in all of these cases, these three impacts have the same crater diameter. So if you just looked on a planet, you'd be like, okay, I have no idea whether it's this lower impact energy, medium, high impact energy, whether it's 6 kilometers a second or 50 kilometers a second, what the impact angle is. But by actually looking at the geochemistry of the material that is in the crater and then around the crater, you can actually disentangle these various pieces and be able to tell exactly what formed that impact crater. Here you can see for the off-axis impact, you actually get impactor material downrange of the impact crater. So this is one thing that we could actually use on the planets to figure out the exact impact conditions that form the large craters that we see. Now looking at crater size, this is a plot of the various scaling relations that are used for small impact craters. when people do experiments or numerical studies, they try to fit the energy and the velocity that they use to what the crater size is and then extrapolate from there. Now granted, these are extrapolated way beyond where they were created, right? These are huge energies that were created somewhere over here is where they're accurate. But if you actually look at it, it gives a huge range when we go to this space. Now our simulations fall around there, which I think is pretty interesting that even though we varied the composition quite significantly, these are clustered pretty tightly. The one large variation is actually these basalt impactors. The slow basalt impactors are a bunch off from the rest of the pack. But other than that, our impacts generally cluster pretty well. And that's to say that the impactor composition doesn't matter very much for the size of crater that is produced. So in general, in order to increase the crater size, you can increase the energy, which is very intuitive. For lower velocities, we get larger craters, and also for more head-on impacts, we get larger craters. The composition has a small effect, and the velocity only has about a 10% effect on what we actually see for crater size. And that's over the range of 6 to 50 kilometers a second. So I already mentioned this a little bit, but how is the crater ellipticity that we look at? Again, here are the, sorry, this is typo. These are the simulations that have been done, I think actually by the Ames gun for different, so this is 75, 85, 88. But you see that even for a 75-degree angle impact, it's very circular, and it's only about 85 degrees that it starts getting elongated, and then at 88 degrees, it basically skips along as it forms it. Now, for our large impacts, we actually see that that's not true. Let's look at the olivine impactors here, and the symbols are the range of impact energies that were simulated. And you see that for the slower impacts, right here, for the most energetic, slower impacts, we actually get a lot of ellipticity, so about 1.2 for intermediate impact angles. So we can get these elongated cavities for rather medium impact angles. Why do we think that there's such a difference between the small impacts where it's always circular and the large impacts where we get this elongation? So these are some simulations, as you see, on a flat surface for smaller impact. And you can see here the shock waves, or the pressures that are achieved in various parts of the impact. Well, when we compare this to ours, the actual pressure contours look very similar. But what's really different is that we have this curved surface. So if you imagine this, and then you curve the surface and cut it off, then these high pressure contours actually get very close to the surface. And so they're capable of excavating the material above them and actually forming this elongated cavity. So this is what we think is happening for why we get this elongation in the cavities for planetary scale impacts, but not for small impacts. Now, moving on to melt. If we just look at the total melt that's produced by these impacts, we find that it's quite a bit. So this is this chart over here. If we look at a global equivalent layer over Mars, so if you spread the entire melt over the surface of all of Mars, how thick of a layer would it be? Well, for the most energy, for head-on impacts where we get the most melt, you get something like 80-kilometer thickness of melt. That would clearly reset the whole surface. We wouldn't see anything of the impact. Story done. This falls into the mega impact size regime, not into the planetary scale impact size regime. But then when we actually look at the map of where this melt is, well, we see that most of the surface is not covered by melt. So this blue stuff is just normal surface, and then the red is melt on top of the surface. So we see that there's a lot of melt inside the cavity. There's some around it. In some cases, especially in the oblique impact, we have some downrange melt. We have melt around the antipodal cavity, but generally, there isn't that much melt over the entire surface. So where does it go? Sorry, I'm going to skip to this. So where does it go? Well, a lot of the melt is actually inside the mantle. Remember that these are very large impacts that actually penetrate a very significant distance into the subsurface of the planet. For the more energetic and head-on ones, they can actually reach the core. They literally reach the core and then bounce off a little bit. If they're made out of olivine, if they're the differentiated impactors, they reach the core, the iron continues on, mingles with the core, the olivine does its own thing. So we can actually deposit a lot of the energy inside the mantle. And so even though there's a lot of total melt produced, a lot of that melt is inside the planet and not on the surface. It does not reset the surface of the planet. So just to go through some of these, for head-on impacts, we have the most melt inside the planet. You see for this undifferentiated case, there's quite a bit. So the dark red is actually the entire thickness from the core mantle boundary to the surface is molten. So you see that's molten. For the iron impactors, you see a lot of melt right in the middle and then not quite as much around the entire cavity. And that's because they're single-minded little impactors. They go straight for the center of the planet because they're so dense. And then there's a whole variation depending on the impactor composition and the energy and velocity of the impacts. I'll do another simulation to show you sort of how it works. So the planet, a quarter has been cut off, or an eighth has been cut off, and you can see this is the core mantle boundary. The impactor comes in. What I want you to notice is that there is a hot area that forms right around here, and then you'll actually see it rotate just from the new rotation that's imparted on the planet. But there's a hot area that forms right around there. So it comes in, does its thing, and then if you saw just play it one more time, the hot area that goes through here and then rotates around. So this is what those plots were effectively showing, that melting all the way down to the core mantle boundary. So moving to the whole planet effects, what do we get in terms of erosion and accretion? And what we see is, so here's just for the differentiated impactors. It's actually similar for other material types. There's some variation, but it's generally similar. If we have low velocity impact, so this is also for just one impact energy. Here we have velocity, here we have impact angle. And what these contours show is how much of the material actually gets accreted or what happens to it. So in the dark blue, the entire impactor gets accreted onto the planet. So if you have a slow head-on impact, the entire impactor gets accreted onto the planet. A little bit escapes, but generally, by far, the vast majority of the impactor actually gets accreted onto the planet. As we increase the impact angle, we actually start missing some of that impactor. Remember how I was saying that the impactor is so large that it can actually miss part of the planet? Well, especially in these 75-degree cases, a good chunk of it just keeps on going. It really does not see the planet, just keeps on going, escapes into space, the whole deal. The impact never happened. And so in those cases, you get a lot of the impactor escaping. So this one line is where a mass equivalent to the impactor mass escaped. That doesn't mean that the whole impactor escaped, that it's only impactor material, but a mass equivalent to the impactor mass escapes. So at this line, there's no net accretion, no net erosion, effectively nothing happens. A bunch of energy gets deposited into the planet, but other than that, effectively nothing happens. So you see that for velocity, that's about 3 times Mars' escape velocity. If the impact velocity of the impactor is more than about 3 times the escape velocity of the planet, there's actually net erosion that's happening. And we find this is pretty similar for the different impactor types. There is some variation, but at about 3 times the planetary escape velocity is the division between having net accretion and net erosion. In these super fast head-on impacts, they actually look really weird, which is why it doesn't really mirror this end. But they effectively go in, they set up a super strong shock wave, and it's like a fountain that comes out of it and just escapes. But in these cases, we can actually eject up to 8 times the mass of the impactor. So now granted, these impactors are smaller because remember, same constant energy, but higher velocity, so they're smaller impactors. So it's still not a huge amount of mass, but effectively, we can eject up to 8 times the mass of the impactor.
What is the significance of the sharp change in direction in the curve at 46 degrees? Is that, it looks almost like a straight line that goes to 46 degrees. We have a very sharp inflection point throughout the whole graph.
I'm not sure.
Well, you've got a limited number of impact angles.
Well, I have 6 impact angles. So here, well, yeah, 45.
You can't draw smooth contours through
Yeah, but there is a change in what's happening, and I can't answer that right now. I think it's something I looked at, but I don't remember exactly what the answer is. So what about planetary rotation? This is the most energetic impact that we simulated. And if we look at the differentiated impactors, which are the most likely, so the red lines, slow velocity impacts at about 45 degrees, which is the most likely impact velocity and impact angle, we can actually give Mars a rotation of about 0.7 days. So faster than it is today. So these are large impacts, granted. They're not close to the moon-forming impact on the Earth, though. Just keep that in mind. But you can actually give planets a very significant rotation with these impacts. And some theories have been put forward that general accretion nets out to the planet being having no net rotation. And then it's effectively the last large impact which contributes most of the rotational period of the planet. And so here we show that you can actually, with these impacts, you can definitely give the planet a very fast rotational rate. And it's not a problem close to what we see on the planets today. So with very little time to go, I'm going to go into the Mars dichotomy question. The Mars dichotomy, as I mentioned, is about 40% of the planetary surface. It's marked by its lower elevation. So it's about 4 kilometers lower than the surrounding area. So the Northern Lowlands are 4 kilometers lower than the Southern Highlands. A more important feature is that actually its crust is about 30 kilometers thinner than the South. So in the South, the average crustal thickness is about 60 kilometers. In the North, it's about 30. So keep that in mind. So something big must have happened. There are two main theories for what happened. One of them is mantle convection. So if you have 1 degree 1 mantle convection, material rising on one side, falling on the other, you can actually erode under that crust and make one side thinner. You can actually also reverse it if you'd like to. You can say that the hotter material buoys it up, and then that material cools more. So you can, with the same sense of convection, you can actually get thinner or thicker crust, depending on exactly what modeling you use, which is interesting. And the other theory is that the dichotomy was formed by 1 or more large impacts. The multiple large impacts is hard to explain because you'd have to have multiple large impacts in the same location of the planet, or at the same general location, rather than all over the planet, so that's difficult to explain. And so let's look at whether 1 single impact could have formed it. This is just a summary of everything that I talked about now. Annular thickening is forming a rim. If we look at this, there's no rim around the dichotomy. There's no special crustal thickening around here. So we can't have a rim, so we can't be anywhere in this blue area. We don't see an antipode to the dichotomy, and so we can't really have impacts that form an antipodal crustal disruption. This area over here is extensive melt. We don't see, if there's extensive melt, it basically means the surface is reset. So a few of our simulations do seem to suggest that the surface may be reset. And then we also, the dichotomy over here, I didn't mention it, it's elliptical. So we also have to explain the fact that it's elliptical. So as we go from higher energy and also higher impact angle, we get ellipticity. So from this graph, we get the sweet spot in the middle that there's no rim, there's no excessive melting, and we get a good ellipticity. So does that actually fit with what we see? So just as an idea, this is the higher range of impacts that we simulated, low impact velocity, intermediate impact angles, and impactors about 2,000 kilometers across. So how does that fit with what we see? Well, this is what we get, and the impact energies, velocities, all of those were set without tinkering them and trying to make them specifically fit the dichotomy. This blue line is our crustal excavation cavity, so the size of the crater, the outlines of the crater. And then this black line overimposed on the Martian crustal thickness is actually the boundary of the dichotomy. So it fits remarkably well. What's more, and I think is really the convincing part of the story, is that all of the required impact conditions are actually what we would expect. So simulations for the last 20, 30 years have shown that this is the range of impactors that we would expect in Mars crossing orbit at the end of accretion. 6 to 10 kilometers a second is the impact velocity that we would expect. Because of dynamical friction, bodies should impact close to their escape velocities. So this is the velocity of impact that we expect anyways, and 45-degree angle is the most likely impact angle. So everything seems to fit together. The size of the cavity, the ellipticity of the cavity, the impact velocity, the angle, the size of the impact, and then as the cherry on top, the rotational period that we get from this impact is a day. So this certainly doesn't prove that this is how dichotomy was created. I think it strongly suggested that this is definitely a viable mechanism to actually form the Mars hemispheric dichotomy. So with that said, I am just going to leave these up actually. I think I went through them in a lot of detail, but and I will leave them up in a second. I just wanted to say thanks to the cluster that I did all of this work at and the people who helped me constantly with making sure everything worked. And Robin Knapp, who was the first to write the code, or she helped with writing the code. And then Paul Asimo, Andy Ingersoll, and Dave Stevenson, who were very helpful in actually getting all of this done and ideas. Thank you.
Margarita, can you go back one slide?
Yeah.
So how are you getting such detail in like around isodus and stuff like that? How did that happen? How do you?
You mean why does it match so well?
Yes.
Magic. So okay. So let me mention this a little more. It matches shockingly well, and I swear this is, I just made the map, I just overlaid it, and it seemed to match amazingly well. We should really remember that a lot has happened to the planet since this impact. So if the dichotomy was formed by a large impact, it happened within the first 50 million years of Mars formation. So 4.5 billion years to do a lot of other stuff to the planet. So for example, you'll see that the boundary here for the dichotomy doesn't include Tharsis. And that's because Tharsis happened afterwards, right? We know that Tharsis happened over a long period of time, way after 50 million years. And so a lot of these features, these volcanoes here came afterwards. A lot of these features are after the dichotomy happened. And I mean, yes, I formed a nice line, but as I mentioned, there are things that are not ideal about the model, right? So strength could play a role. Things relaxing in and out of place could play a role. I wouldn't take the exact little details of that blue line too seriously.
And did the impactor come from this direction or this direction?
The impactor came from this direction.
Okay. So what we're seeing is sort of some excavation lobes almost of this sort of magnitude. Okay.
Yeah.
All right.
Yeah. And something I forgot to mention is you might wonder, well, how do you get a 45-degree impact at the pole, given that everything should be in about the same plane? That's actually not an issue because we're pretty certain that Mars has gone through true polar wander. And so the impact was probably much closer to the equator, and then the crust of the planet reoriented.
What do you think, how do you think the subsurface melt from an impact of that scale evolved afterward? What do you think the implications of the melt were?
It's a very, very good question, and that's something that we want to look at in the future. So one reason why we actually wanted to look at the amount of subsurface melt is that you imagine Mars started with sort of a molten mantle ballpark. If you melt the entire thickness of the mantle again, well, you're going to create crust that's probably going to be of similar thickness as the surrounding crust, which means you're not going to see that crater again, right? If we're thinking of observations that we make of the planets, if you form new crust, which is about the same thickness as the pre-impact crust, you're not really going to be able to tell that an impact happened there. So that was one of the reasons that we wanted to look at this. Now, of course, the story is not that simple at all. And whenever I've talked to people who actually do crustal formation and mantle convection, all kinds of studies, it's just not that simple. They refuse to give me an answer without actually trying to do a detailed model, because it depends on the cooling history, on whether you have convection, on whether you get a stagnant lid at the top, on a million other things. So as a very huge hand-waving argument, if you melt all the way down to the entire thickness of the mantle, you can expect a crustal thickness that's about the pre-impact crustal thickness. Very hand wavy.
I've got a billion questions. Do you expect, after all that's taken place since this event, is there anything exposed on the surface in the northern lowlands, any outcrops or something like that that would kind of hint at at least the mineralogy, exposure of mantle material and stuff, olivine-rich stuff there? Or is it all just completely covered over with, more recent geology?
Well, you should have a lot of crust forming in that area, so I'm not sure that you would have a lot of mantle material exposed. And we also know there's a lot of just geologic material that has gone into the north, so I would be surprised if you could really see.
So it could still subsequently be flooded, for instance, and you'd have you'd have ocean?
Oh yeah, I mean,
ocean
this is
thing.
the first 50
Yeah.
million years, right? I mean,
And
yeah.
how about the dynamo? If there's an active dynamo going on, this is a profound day for that dynamo too. Is it?
Yeah, so there has been
I wonder if
actually-
anybody's looked at what
Yes, they
impact
have.
it could. Okay.
There've been a bunch of papers looking at how this large impact could affect either form a dynamo, stop a dynamo, change a dynamo. It really, I mean, the parameters, we don't know any of the parameters. So depending on how you tune them seems to decide what result you get. As I mentioned, there have been both turning on the dynamo and turning off the dynamo and explaining a dynamo only in the southern hemisphere, so making it asymmetrical. So it seems very dependent on what model parameters you use. Is my understanding of it, at least.
So you showed one simulation that was a good fit
Yep.
for the dichotomy, but you ran a bunch of simulations. So how many of them were good matches, and how many of them had results that did not produce a dichotomy?
So I did a huge range of simulations. So it's not surprising that most of them didn't. I mean, all the stuff down here, we never expect them to do. The crater diameters around here are 4,000 kilometers, 6,000 kilometers. Dichotomy is 10,000, so we never expect them to. This is basically the range that did work. So most of the combinations within this range, so there are 2 impact energies here, 2 velocities, and 3 impact angles. Most of the combinations of these did work, were close.
So
Yeah.
fraction
Oh, so this would be what, like 15 simulations out of, yeah. I mean, the 1,500 or so also include the different resolution simulations. So let's say out of 1,000 or something.
Did any of the ejected material get captured into orbit?
Yes. So we do get material captured into orbit, and what's interesting is that it's actually, it's very consistent. So the amount of material captured in orbit as a fraction of the impactor mass is constant for all energies, which is very interesting. So it scales very linearly with the whole process. I didn't mention it because the amount of material is still small enough that it's the equivalent of 10 or 15 particles going into orbit. And because the trend is so consistent down to 1 or 2 particles, I'm reasonably confident in it, but it's very hard to actually make conclusions about 15 particles going into orbit. And I know the follow-up question will be, will they form a moon? And again, because there are only 15 particles, it's really hard to tell. You could imagine that if those were, again, we can't really tell if it's a large chunk, 120 kilometer chunk being ejected, or whether they're large enough forces to have those chunks go into orbit. But in those cases, you could imagine that staying in orbit for a while.
So could it be the origin of Phobos and Deimos?
So my understanding is that those are captured objects. I know a recent paper came out saying that they were ejected objects, and I haven't had a chance to read the paper, so I can't comment on that.
That was based on mineralogy, wasn't it, I think, rather than rotation of the
Yeah.
bodies and stuff.
So my question are on the 2 other terrestrial planets in the solar system. So Venus rotates very slowly. I mean, it has a day longer than this year, and it's retrograde. But you could argue that it's rotating so slowly, it's effectively not rotating. That it's so perhaps it escaped a large late impactor?
Venus is a completely different story. Actually, Andy Ingersoll was one of the people who wrote the paper a while back saying that the atmosphere of Venus is actually capable of slowing it down to its current rotational rate, even starting at 1 day or even faster, I believe. So for a 1-day rotation, it could slow it down in 300 million years.
Sorry, what's the mechanism for that?
The atmosphere, tidal dissipation in the atmosphere.
Really? I mean, so you mean from the sun?
Yes, I believe.
Wow. So the sun's
sun.
tidal bulge on the atmosphere will actually.
Well, it's also the friction on the atmosphere. I can't remember the details right now.
Or the friction? Wow. Okay, so my second question is on Mercury.
Yeah.
Which has the second slowest rotation in the solar system of a major planet, and its core seems so large that a lot of people think that its outer layers were removed by a late impact. Has anybody done any work on that?
Yeah, so Eric Asbach has actually simulated a large impact stripping the mantle off of Mercury and doing that. In terms of the rotation rate, again, this is not my expertise, but I thought that because Mercury is so close to the sun, you can actually slow it down significantly just from tidal dissipation.
So it's just in a 3-to-2 resonance, and it got tidally, it's sort of tidally locked, and so it could have started out with any initial rotation. Okay.
Yeah. Mars is harder because it's so far that what we see today on Mars probably was always there.
Margarita, thanks very much for being our speaker today. And this is a special SETIcon glass.
Thank you.
As a memento of your talk today. So if you'll join me in thanking Margarita for a great talk.